So hello and welcome to another week of the Algebra-II course offered by NPTEL NOC 23MA14. I'm one of the PMRFTs for this course. My name is Shubhajit Das and this is week 10. So as we keep doing every week, we'll be solving problems based on the assignments of the particular week. And I do hope that you are also attending Ajay Prajapati's sessions. And so without much ado, we'll start. Okay, so this week you have been continuing with your study of tensor products and some of their properties. Tensor products of modules over a ring and some of their properties. So we'll continue doing this. So let us read the first question. The first question says that you have to choose all the correct answers from these four options. So the first option is saying that the dimension of Rn tensored over R with Rm is m plus n. The second one says that the dimension of Rn tensored over R with Rm is mn. The third one says that 2 over 3 tensored with 3 is 1 tensored with 2 in the tensor product R tensored over Q with R. And finally, option D says that A tensored with B is equal to 1 tensored with AB in R tensored over Q with R for any AB in R. So you need to figure out which of these options are correct. Okay. So without any problem, we can directly observe that option A is clearly correct. Now we know that in general for modules M and N over a ring A, if M is generated by Xi, a set Xi in M, and N is generated by a set Yi in N, then Xi tensored Yj, these elementary scalars will generate M tensored over An. Okay. So what I mean by this, this in particular also implies, you have to do some more work, and this will then imply that if V and W are vector spaces over a field F of dimensions M and N respectively, then the dimension of their tensor product over F is precisely M times N. Okay. So we can, using this we can say directly that the dimension of Rn tensored over R with Rm is Mn. But let's give a more concrete proof of this. So we know, so last week we had seen that tensor products, suppose N is a fixed A module, taking the tensor product with N is a functor of the category of R modules into the category of R modules, and we saw clearly that this functor is actually left adjoint to the Hom functor, which is again from R mod into R mod in the opposite direction as this functor. So the other functor, the Hom functor and this particular functor, they form an adjoint pair of functors, and the tensor product functor is a left adjoint to this Hom functor. So the Hom functor is a right adjoint. Now a consequence of this is that Hom, the co-representable Hom functor, the covariant representable Hom functor, Hom n comma bar. Okay, so you are looking from R mod into R mod, so it sends any R module M onto the R module of all morphisms of n into M. Anyways, the point is that the tensor product functor is clearly a left adjoint, and therefore we know that left adjoints preserve co-limits. In particular, they will preserve direct sums, which are co-products, particular types of co-limits in the domain category of the tensor product functor. So the point is that tensor products distribute over direct sums. This is what we need. So we know tensor products distribute over direct sums, right? This is something known to us. Thus R power n tensored over R with R power m can be written as direct sum of n copies of R tensored over R with R power m, which is isomorphic to uh, the direct sum of n copies of r tensored over r with r power m, which is isomorphic to direct sum of n copies of r power m. Since we know that r tensored over r with r power m is just r power m, and this is just isomorphic to r power m. Okay, so B is certainly correct. And what about C? C is saying that, so inside so in r tensored over q with r, 2 over 3 tensored with 3. So keep in mind that the tensor product is taken over q, which means that you can switch scalars from one side to another side by or from this side to this side, or from the so you can switch scalars in elementary scale, in elementary tensors, right? That is, you can switch the scalar either from this side to this side, or you can switch the scalar from this side to this side, right? So in the tensor product r tensored over q with r, 2 over 3 tensored with 3 can be written as so this can be written as so this can be written as 1 tensored with 2 over 3 times 3, which is equal to 1 tensored with 2. So it's clearly correct. And option D is incorrect, as I mean, you can just, as a can be an irrational number, right? And then you won't be able to switch a to the other side, okay? Because you can only switch scalars from the ring, right? And the ring over which you are taking the modules is q. So it can be an irrational number, and then you won't be able to switch. And since B is correct, therefore A is also incorrect, right? So A is incorrect. As B is correct. So this is incorrect, this is correct, this is correct, this is incorrect. Okay, so let us move on to our next problem. So let V be a vector space over the rational numbers and W be a vector space over the real numbers. Then you need to choose the correct ones. So option A is saying that V tensored over Q with R. So note that V is a vector space over Q, R is a vector space over Q. You can take the tensor product. So this is an R module. Option B says that HOM R V tensored over Q with R, comma W is isomorphic to HOM Q V with W. So what this says is that taking tensor product over Q with R is actually so note that W is a vector space over R, hence it's a vector space over Q as well. Therefore you can look at the space, I mean you can look at the set of all morphisms from V to W, right? You can look at the set of all morphisms of V into W, the morphisms in the category of Q vector spaces from V to W, right? That is the morphisms with domain V and codomain W. in the category of Q vector spaces. So what this says essentially is that taking tensor product over R with Q, this is a taking tensor product over Q with R, this is a functor from the category of Q vector spaces to the category of R vector spaces, and so and on the other and in the opposite direction you have this restriction of scalars functor, right? So you have a functor in the opposite direction, which is from the category of R modules into the category, R vector spaces into the category of Q vector spaces. That is your restriction of scalars functor. So what you do is, so you have an inclusion of Q into R. Anything which is any R module is therefore by restriction of scalars a Q module, right? So what this essentially says that the extension of scalars functor, that is taking tensor over Q with R and the restriction of scalars functor, these two form an adjoint pair of these two form an adjoint pair of functors, right? So you have two functors, these two functors are in opposite directions, and what this says is that there is an adjunction between the two, right? That is the two functors form an adjoint pair of functors. This is clearly correct, we'll see. Option C says that form or V tensored over Q with R comma W is isomorphic to form. Oh, okay, so option B was not isomorphic. Option C is they are isomorphic. And option D says V tensored over Q with R is isomorphic to V. Okay. Okay, so let us solve this problem. Now, so just recall the following fact, that if A, so recall that if yeah, sorry about that. So recall that if A to B, if you have a ring homomorphism F, then there are functors, then there are two functors. So from A mod, the category of R modules, into the category of B modules, you have one functor, right, which is the extension of scalars functor. So what you do is you take an A module, take its tensor product over A with B. So B is a B module, in particular B therefore is an A module as well. So you can take tensor product over A with B, and you have a functor in the opposite direction, so which is the restriction of scalars functor. Functor, right? And these two functors, if you recall, form an adjoint pair of functors. That is, there is an adjunction between the first functor and the second functor. The first functor, the tensor product functor, is a left adjoint, while the second functor is a right adjoint. Okay. So the first functor, the extension of scalars functor is a left adjoint of the adjoint pair, and the restriction of scalars functor is a left adjoint in the adjoint pair. So there is an adjunction between the two functors, and And what else was I going to say? Yeah, so this is what the deal is. So in particular, so so this is an adjoint pair of functors, pair of functors, right? This one is the left adjoint of the adjoint pair, left adjoint in the adjunction, and this one is the right adjoint in the adjunction. And so we can say that for any, or maybe we'll put it later, so we can say that B mod I'm sorry, B mod M tensored over A with B comma N is in bijection, is in natural bijection. There is a natural bijection between this and A mod. So there is a bijection of the first set. So there is a bijection of the first set onto the second set, the set of all morphisms in the category of A modules from from M to N. So yeah, so this is naturally in M belonging to our first category A mod, and N belonging to our second category B mod. So what do I mean by naturality of the bijection? By naturality I mean that if you take, instead of M, if you take some A module M prime, and instead of N, if you take some B module N prime, and if you take maps from you take a mapping of M into M prime, and you take another mapping of N into N prime in the appropriate categories, then you should be able to get out you should be able to get a diagram out of this, right? So so you should have a square, so to say, you should have a square where the horizontal arrows are just these bijections, these canonical bijections which we are talking about, and the vertical arrows will be given, will be functorial images of the arrow from M to M prime and the arrow from N to N prime. Okay, so that square will commit. Okay, so what naturality means here, in general naturality, what naturality means is that, so a collection of arrows, so you know what natural transformations already are, right? So naturality essentially means that, so you have a parameterized collection of arrows which is parameterized by objects in some category. So naturality means that these arrows are defined in the same way for all objects in the category. They are defined uniformly across all objects in the category. Okay, they don't depend on any arbitrary choices. They are defined in the same manner. Okay, for all objects in the category. So for, let's say, for the object, so for some object, I mean for let's say for the object A, this for the object A, let's say this morphism, this arrow is defined in a particular way, and then if you replace A by some object A prime, then the corresponding arrow for A prime will also be defined in the same way. This is what naturality essentially means. Okay. So this is what we know, and therefore, so A is correct. That is, V tensored over Q with R is indeed an R module. This is the essence of the extension of scalars functor, right? We extension of scalars functor. This is what we saw previous week, right? That V tensored over Q with R is indeed an R module. So A is correct by extension of scalars. How will you put the R module structure on the tensor product V tensored over Q with R? You just take an element, an arbitrary element in V tensored over Q with R, and you take an arbitrary element in R, a scalar in R. You just multiply. Let's say you have taken an elementary tensor X tensored Y in the tensor product, and suppose you have taken some real number r, so x tensor y dot r will be defined to be x tensor with yr. Okay, this is your r module structure. So the A is correct. What about B? B is incorrect, as C will be correct, right? We know that the extension of scalars functor and the restriction of scalars functor form an adjoint pair of functors, and therefore or certainly C will be correct. In fact, not only is C correct, something more is true. You know that these bijections are natural in the vector space V belonging to Q modules, and the object V belonging to Q mod and the object W belonging to R mod. So these are natural bijections. Okay, so C is clearly correct. So C is correct, and hence B is incorrect. And finally D is incorrect, right? D is incorrect, as for V equal to Q in Q mod, Q tensored over Q with R is isomorphic to, certainly isomorphic to R, which is not isomorphic to V equal to Q, right, as Q modules or Q vector spaces. Because if R and Q are isomorphic as Q vector spaces, then their dimensions would be same over Q, but the dimension of Q over Q is 1. I mean, one of them is countable, the other one is uncountable. You can just use this argument. And then isomorphism in the category of vector spaces will also be an isomorphism in the category of sets. That is, it will be a bijection in particular. So it should preserve cardinality as well. So if you have an isomorphism of R onto Q, then this isomorphism preserves cardinality. So that R is uncountable would mean Q is uncountable, which is an impossibility. So option 2 is, so certainly option D is incorrect. Option C is correct, option A is correct, option B is incorrect. So let us move on to our next problem. So question 3. So let F be a mapping of C power n into C. So F maps C power n into C. F is a mapping of C power n into C such that if P is equal to C1, C2, dot up to Cn, then F of P is equal to the sum of Ci's. Okay. And you define another mapping of C power n, but now into C2, okay, such that T of P is equal to Fp, which is an element of C, times 2, 3. Then you need to choose the correct answers. A says that T is C linear as a mapping of Cn into C2. Option B says that the dimension of Hom C Cn, C2 is 2n. So in the category of C vector spaces, if you look at the Hom object from C power n to C2, that is, if you look at the collection of all morphisms of C power n into C2, collection of all morphisms from C power n to C2, and this is a vector space over C, and they are saying that the dimension, and they are saying that that its dimension is 2n. Option C says that Cn star. What is Cn star? It's just Hom Cn comma C, right? You just, it's the dual space of Cn, right? You just look at the you just look at all the linear maps of Cn into C. So Hom C Cn comma C, from Cn to C, Hom object from Cn to C, Hom object from Cn to C. Yeah, this tensored over C with C2 is isomorphic to Hom C Cn comma C2. Option D says that the image of T in Cn okay, so this is not clear to me. I think they have written something wrong. Over C with C2 is okay, is F tensored with 2 comma 3. Okay, so this seems to be a big problem, so let's solve it. So firstly, you are given a linear mapping of Cn into C linear mapping. Firstly you are given a mapping of Cn into C, which sends any point C1 up to Cn onto the sum of all Ci's, right? And you define a mapping T of Cn into C2 such that T of P is equal to f of P times 2 comma 3. Then you need to choose all the correct options. So firstly it says that T is C linear as a mapping of Cn into C2, which means that T of P plus W will be T of P plus T of W. So is this correct? Let us quickly see this. T of P plus, let's say, Q is f of P plus Q times 2 comma 3, right? And this is f of P plus f of Q times 2 comma 3 and this is f of P times 2 comma 3 plus f of Q times 2 comma 3 for all PQ in Cn, and T of lambda times P is equal to f of lambda times P times 2 comma 3, which is equal to lambda times f of P times 2 comma 3 for all lambda in C comma P in Cn. So the point is that f is a linear mapping, and therefore this T will also be a linear mapping. So A is correct. What about option B? Option B says that dimension of this Hom space from Cn to C2 is 2n. Okay, so this is so you look at all the C linear maps of Cn into C2, and the dimension is 2n. This is certainly correct. B is correct, as we already know from elementary linear algebra that Homc Cn comma C2 is isomorphic as a C vector space to the space of all. So you are looking at linear maps from Cn to linear maps. You are looking at linear maps from Cn to C2, which means that you are looking at matrices, right? You are looking at 2 cross n matrices. So this is C. I forgot what was the notation, but I guess it is M2 cross n over C, right? So the dimension is clearly 2n. Option C says that Cn star tensored over C with C2 is isomorphic to Hom C Cn comma C2, right? So how are you going to show this? That Cn star tensored over C with C2 is isomorphic to Hom C Cn comma C2. So indeed this is okay. So this is easy if you use the property of the tensor product. So Cn star tensored over C with C2, this you know is isomorphic to Cn star tensored over C with C direct sum C, and you know that tensor products distribute over direct sums. So this is Cn star, I mean you can write this as direct sum Cn star tensored over C with C, I mean yeah, you can write this as this direct sum with Cn star tensored over C with C, right, which is isomorphic to therefore Cn star direct sum Cn star which is therefore isomorphic to Hom Cn comma C direct sum. So this is over C, looking at in the category of C vector spaces. So this direct sum with Hom over C Cn comma C, which using the properties of Hom, so the functor Hom over so the functor, the representable functor Hom Cn comma dash, okay, this functor preserves limits, right? And I mean this preserves in particular it preserves products, and a finite direct sum in the category of vector spaces over any field is the same as a finite direct product, right? Direct sums and direct products are isomorphic. Finite products are the same as finite co-products, okay. So the point is this, that Hom, this is isomorphic to Hom Cn comma C cross Hom Cn comma C, right, which is isomorphic to Hom Cn comma C cross C. This is where we are using the fact that the Hom Cn functor, the covariant representable functor Hom Cn will preserve products, okay. So and this is just Hom C Cn comma C2, so that C is correct. And option D says that if you look at a particular isomorphism, so we have been following a chain of isomorphisms, we can use them to obtain an isomorphism of this onto, so this arrow is an isomorphism right, in this category this arrow is an isomorphism, right, that is this arrow is an invertible arrow, right. This arrow possesses an inverse, right, in this category. That is this morphism, or this arrow is an isomorphism in this category of this onto Okay, so we need a map in the opposite direction. Actually, it doesn't matter. We can just take this, and we can take Cn comma C2, and we take the element F, which sorry, we take the element T here. Okay, this is an isomorphism, means that you have a map in the opposite direction. You have a mapping in the opposite direction, which is an inverse of this map, right? So, and this mapping will map T to something onto something. So the claim is that the image of T is F tensor with 2 comma 3. Okay, so if we can just find out what our isomorphism is, we are done, right? So so we define, so we try to understand the isomorphism. So what this isomorphism does essentially is that it picks up any element here in Cn star tensored over C. So any arbitrary element will be a sum of elementary tensors, and a single elementary tensor will be of the form M tensored with some complex number a comma b. And where should you map this to? So F is from Cn to C, right? So it should map to some F hat, which is a mapping of Cn into C2, right? And it should take some P, and it should map P onto what? So where should this map P onto? So F is a linear map, and this should map P onto, yeah, you want a linear map, right? Where should you map this to? Yeah, I guess this would be F of ABP. I guess this would work, right? Because no, I guess this would be you need an element of C2, right? Yeah, so what am I thinking? FP times, yeah, right, you need an element of C2. You need to map it into C2, not into C, right? So if hat is a mapping of Cn into C2, so it should map P onto F of P times AB. This is what it should map to. So is an isomorphism. So we first, yeah, we can remove the isomorphism sign. Is an isomorph. This morphism is an isomorphism. So yeah, let me be very precise. So the morphism, so this morphism is an isomorphism, right, of C vector spaces, right? The isomorphism that we are talking about. So this morphism is an isomorphism. So the image of T, thus the image of T under, so T is an element in the codomain of this morphism, right? T is an element. So capital T is a linear mapping of Cn into C2, which means that capital T is an element in the codomain of this morphism, right? And that is the target of this morphism. The target of this morphism, or the codomain of this morphism, and therefore the image of T under the inverse of this isomorphism. This is an isomorphism, it therefore possesses an inverse. Okay, this arrow is invertible, it has an inverse. So under the inverse map, under the inverse map, or inverse arrow, or inverse morphism, whatever you'd like to call it, right? Morphism, right, from Cn comma C2 into Cn star tensored over C with C2, right, is therefore so what was T? T was T of P was f of P times 2 comma 3. So is this image is clearly f tensored with 2 comma 3. Why? Because f tensored with 2 comma 3 under the forward mapping will get mapped onto T, and therefore since this is the inverse morphism, therefore the image of T will clearly be this. So this proves statement 3. I mean question 3. Let's move on to our next problem. So yeah, so which of the following were correct? So certainly T is C linear, dimension is this is this, and this is this. So each one of the options are correct, right? Right, so let us move on to our next problem. Question 4. Let A n cross m and B m cross n be matrices over C, and let T be a mapping, be a morphism of Cm tensored over C Cn so let so let T be a morphism of the object Cm tensored over with C, tensored over C with Cn into, so let T be a morphism of this object into Cn tensored over C with Cm, okay, be given by T of little x tensored little y is Ax. So if x is an element in Cm and A is an n cross m matrix, okay, then Ax is in Cn, Ax tensored with By, right, for all x in Cm comma y in Cn, okay. So we need to choose the correct options. Option A says that T is Z linear but not C linear. B says that T is, oops, sorry. is C linear. Option C says that if little m is equal to little m, then T is an isomorphism. And option D says that Cm tensored over C with Cn is isomorphic to Cmn. Now option D is clearly correct as we have previously seen. So solution D is clearly correct as seen in the previous problems. What about option A? I mean option A or option B? So T is a right. What about option A or option B? So T is a mapping of this object into the T is a mapping of Cm tensored with Cn of this object into Cn tensored with Cm, right? T is a mapping, and T is a morphism of this object into this object, right? So so the point is whether T is C linear or not, right? Now you can take this mapping of Cm cross Cn of the set Cm cross Cn into Cn tensored with Cm, okay? That does this job. So what I'm trying to say is B is correct as T is induced by the C bilinear mapping. By the T is induced by the C bilinear mapping. Induced by the C bilinear mapping from Cm cross Cn into Cn tensored with Cn tensored over C with Cm, which sends x comma y. This mapping is mapping x comma y onto Ax tensored with By. Right? This map is clearly bilinear, right? Because taking product with a matrix A is linear. Similarly, taking product with a matrix B is linear, and you have tensor product between them. Ax tensored, so Ax, so A of bar tensored with B of bar. This will be a bilinear mapping, right? Yeah, this A of bar tensored with B of bar. This will be a bilinear mapping of Cm cross Cn into Cn tensored over C with Cm, right? And hence this induces a unique C linear mapping of Cm tensored over C with Cn into Cn tensored over C with Cm, which sends x tensored y onto this. Okay, so this is what the this is precisely what the map T is. So so T is induced by the C bilinear mapping of this into this using the universal property of the tensor product. So B is clearly correct. So and hence A is incorrect. Now C is incorrect because even if M is equal to M, it could happen as uh, A and B can be non-invertible matrices, right? So what happens in the case that A and B are non-invertible matrices? X, even though X and Y are non-zero each, so that X tensor Y will be non-zero in the tensor product. It could happen that AX is 0, BY is 0, so that it's not an isomorphism. So C is incorrect and option D is correct, as we clearly saw. So this finishes this problem. Let us move on to our next one. So question 5 says that let M be an RS bimodule and N be an ST bimodule. So R, S and T are just rings, not necessarily commutative. M is an RS bimodule, which means that M can be thought of as a, so which means that M is a left R module as well as a right S module, and the two structures are compatible. Similarly, N is a left S module and a right T module, and the two structures are compatible. And you can alternatively think of this RS bimodule as a functor from, okay, so you don't know what p-additive categories are, so it will not make much sense to talk about it now. Okay, so yeah, so what I was saying is yeah, okay, so yeah, so we need to choose the correct options. So A is saying that M tensored over S with N is an SS bimodule. Okay. Option B says that M tensored over S. So note that M is a right S module and N is a left S module, right? So you can so M is a right S module, N is a left S module, and hence you can talk about taking the tensor product M tensored over S with N, which is just an abelian group. But M is a left R module, N is a right T module. So M tensored over N tensored over S with N will be an RT bimodule. Okay. So this second one is saying this is an RS bimodule. Third one is saying that M tensored over S with N is an ST bimodule, and option D says that M tensored over S with N is an RT bimodule. So as we said, only the option D will be correct. So solution D is correct only as the left R module structure on M induces a left R module structure on M tensored over Sn, and the right T module structure on M induces a right T module structure on M tensor over S with M, and the two structures will be compatible, so that option D is correct. So what I mean by compatibility is, and so little r times any element of this is a sum of elementary scalars, but we'll just write only one elementary scalars, because the other thing, I mean, if you take sum, that is implied from this. So x r times x tensor y, or maybe summation, we'll write it in its whole, times little t. So this is equal to r times sum xi tensor yi. I'm sorry, yeah, dot t. Yeah. For all r in r, t in t, and sum xi tensor yi in M tensor over S with M. Of course, finite sums. So option D is correct. Option C, option B, option A, all three are incorrect. Right. So let us move on to the next problem. So question 6. So let I be an ideal of a commutative ring R and M be an R module. Choose all the correct options. So option A says that R over I, R modulo I tensored over R with M, is isomorphic to M mod IM. Option B says that R mod I tensored over R with M is isomorphic to M. Option C says that R tensored over R with M mod IM is isomorphic to M mod IM. And option D says that R tensored over R with M mod IM is isomorphic to M. Okay, so which of all these will be correct? Solution. Okay, so recall that the tensoring over R with M is left adjoint to to the Hom functor, right, represented by M, Hom R M comma bar. Okay, so this is a left adjoint. This is what the symbol means. There is an adjunction adjunction between these two functors, with the tensor product functor being a left adjoint, and the Hom functor. Yeah, so this turnstile notation denotes adjunction. This is what we write to denote that one functor is adjoint to the other functor. So there is an adjunction between the two functors, right, with this being a left adjoint and this being a right adjoint. And right adjoint, I mean left adjoints preserve all co-limits, right? Whatever co-limits are in their domain, those co-limits are preserved in the codomain. Okay, so left adjoints preserve all co-limits, right? Right, and hence left adjoint functors uh, uh, left adjoint left adjoint functors uh, so that is a functor from one category. So what I'm trying to say is, suppose f is a functor, and the direction of the functor f is from a category C into a category D, and assume that this functor f does have a right adjoint. That is, assume that the functor f is a left adjoint of some adjoint pair of functors or of some adjunction. Then this functor f will preserve all co-limits. Okay, and hence, since it preserves all co-limits, it in particular preserves co-kernels, right? That is co-equalizers, and hence in particular it preserves co-kernels. And since it preserves co-kernels, hence it will be a right exact functor. So what I'm trying to say is, hence this functor, which is maps, this functor mapping R mod into R mod. So this functor mapping, hence this functor tensor product over R with M, hence this functor mapping R mod into R mod is a right exact functor. Functor, which means that it preserves right exactness of sequences. Okay. Thus, I hope you have done this, what right exactness means. Thus, I to R mod I to 0 is right exact in the domain R mod. Implies that that the functor carries this right exact sequence to a right exact sequence, since the functor is defined to be since the functor is a right exact functor. Therefore, by definition, this is just the same thing as saying that this functor carries right exact sequences onto right exact sequences. That is this functor preserves right exactness. That is, the image of any right exact sequence in the domain is a right exact sequence in the codomain, right, in the target. So I tensored over R with M to R tensored over R with M to R mod I tensored over R with M to 0, right? This is right exact in the target R mod. Now this is isomorphic to M, right? And what is this mapping? This map sends any little a tensored with little x onto little a tensored with little x, which via this isomorphism we know that there is a natural isomorphism or a canonical isomorphism of this onto M, namely that because of the fact that R is actually a unit object in the something called a monoidal category of R modules, right? So you via the left uniter, or let's not get into all those complications, you just have an isomorphism of this onto this, and a tensor x is mapped onto ax. Okay, so what I'm trying to say is that the image of what I'm trying to say is that Im, which is equal to the image of this map from I tensored over Rm into M, right, is equal to the kernel of the map from M into R mod I tensored over R with M. And we know that this map is an epimorphism, right, in the category of R modules. This is an epimorphism because the above sequence is an exact sequence. Okay, so this is an epimorphism. So what I mean by an epimorphism in the category of R modules is precisely a morphism in the category of R modules, that is a mapping of one module into another module, which is a surjection. So it's a surjective morphism, surjective homomorphism. That is what an epimorphism is in the category of R modules. Right, so which implies that M mod, the kernel which is Im, is isomorphic to R mod I tensored over R with M. Okay, so option A is correct, and therefore option B, so A is correct, and hence B is not correct, because otherwise M would always be isomorphic to M mod Im, which is not true, certainly always. Option C is again correct, clearly, as R tensored over R with any R module is always that is isomorphic to that R module, canonically isomorphic, and D is therefore not correct. Right, so what I am trying to say is A is correct and C is correct, this is incorrect and this is incorrect. So what about question, next problem? So let M in P be finite dimensional vector spaces. Then form M tensored with N comma P that is all that is a Hom set from M tensored into P. The set of all morphisms from M tensored N into P is isomorphic to Hom M comma Hom Hom M comma N star tensored with P. Okay, this is what we need to show. So I mean, this is, we need to claim whether this is true or false. Okay, so the claim is that this is indeed true. So solution, this is true. Okay, firstly, since bar tensored over the base field with M is a left adjoint to Hom N comma bar, the representative functor Hom N comma bar. This is popularly known as a Hom tensor adjunction, which is true in general for R modules. Okay, so which we have been using so far. Right, so this functor is left adjoint to the Hom functor. The Hom functor is a right adjoint. So what we can say is, hence Hom M tensor N comma P is actually isomorphic to Hom M comma comma mm, home n comma p, right? And these are not only isomorphic, this is true naturally in M belonging to so this is true naturally, so over the same field we are taking vector spaces. So naturally in the vector spaces M and P, in fact this is also naturally in something called, this is due to something called parameterized adjunctions. Anyways, so we have this. Now we need to prove that the second set is actually isomorphic to uh, so what I'm trying to say is hom n comma p is actually isomorphic to, so we finally show that hom n comma p uh, so this is isomorphic to n star tensor with p. Okay, so let f be the base field, common base field, so let f be the common base field, then P being a finite dimensional vector space implies P is isomorphic to some f power n, that is direct sum of copies of f. Thus n star, or maybe hom f n comma p is equal to hom f n comma f power n, right, which is isomorphic to hom. So this direct sum is again a product, and hom, the covariant hom functor, preserves limits, right? So it will so it preserves limits means that it changes it preserves limits means that it preserves products in particular, right? So this is hom f n comma product of f I running from 1 to n, which is isomorphic to, therefore the product of I running from 1 to n hom f n comma f, right, which is isomorphic to the direct sum of I running from 1 to n. Finite products are the same as finite direct sums, that is finite products are the same as finite co-products. Okay, so this is isomorphic to n star, which is isomorphic to direct sum I running from 1 to n star tensored over f with f, right, which is isomorphic to, again tensor products commute with direct sums, so this is isomorphic to n star tensored over f with direct sum I running from 1 to n f, which is therefore isomorphic to n star tensored over f with f power n, which is isomorphic to n star tensored over f with p, precisely what we wanted, right? So thus there is an isomorphism from form n comma p to n star tensored over f with p. Okay, and since functors preserve isomorphisms, so assume that f is a functor from a category C into a category T, and assume that little f is a morphism in the category C, which is an isomorphism. Then so what I'm trying to say is that assume that capital F is a functor from a category C into a category T, and so what I'm so what I'm trying to say is this, that assume that capital F is a functor from a category C into a category T, which means that which means in particular that for any morphism F, since for any morphism F in the first category C, the functor capital F will map F onto a morphism in the category T. This is just the base. This is just the definition of a functor. It maps objects to objects and arrows to arrows. Now, using the functoriality of a functor, using the fact that F preserves the category structure, you can easily prove that a functor in particular carries isomorphisms to isomorphisms, right? Right? So functors preserve isomorphisms. Hence, what you can say is hom m comma hom n comma p to hom m comma n star tensored over f with p. This map is an isomorphism. I mean the image of the. So let's call this f, right? So hom m comma f, right, is this this arrow, that is this morphism, is an isomorphism. The image arrow, the image of the arrow f, which is the arrow hom mf, the image arrow is actually the image. So the image arrow, that is the image morphism, is actually an isomorphism. And thus you indeed have hom m tensored with n comma p is isomorphic to hom, sorry, which is isomorphic to hom, sorry, yeah, hom m comma hom n comma p is isomorphic to hom m comma n star tensored with p. And finally we are left with one other problem. So let f map z mod into R mod. So f is a mapping of z mod into R mod, okay, which is defined on the objects as follows. It maps m to m tensored. So R is a commutative ring, or maybe any ring, I guess. So which maps oh sorry, so not R mod, it's R mod, I mean reals, okay. So which means that it's in particular commutative. So it maps m, which is in z mod onto R tensored over z with m, which is an element of R mod, as we know by extension of scalars. It maps n onto R tensored over z with n, and maps any arrow little f in the category onto an arrow which is 1R, the identity or R tensored with f, which is an arrow in R mod. Okay, so f of f is equal to 1R tensored with f. So the claim is that f is a functor or not. Then I mean this is very easy. I mean there was no need to write this problem. And f is a functor. option E is true and option B is false. So we clearly know this is true. So solution, we clearly know that this is true, as capital F is just the extension of scalar's function. Yeah, scalar's function R tensored over Z with bar along the ring morphism, or the ring arrow in the category of all rings, along the ring morphism, um, the ring morphism along the ring morphism, yeah, along the ring morphism, that is along the morphism, from Z into R, which is, so I've curved the tail of the arrow. So it was a straight arrow, right? So instead of taking a straight arrow, observe that that for the tail of the arrow I've curved the tail, right? Which means that I'm writing, so instead of taking a straight tail, I'm curving the tail. So I'm writing like this. The tail has been curved. The tail of the arrow has been curved, which means that this is an inclusion map. Okay. So this is inclusion. Okay. So this is F is just the extension of scalar's function, and hence this is correct. So option E is, I mean, it's true. Yeah. Okay. And this finishes the problems for this week. So if you have any questions, you can always email me. I'll just write down my email ID, which is Shubhajit @iisc.ac.in. Okay. And yeah, that's all for this week. And if you have any questions, if you have any questions, you can always ask me. Okay, so we can stop. So see you next week. So I'll stop the recording.